Anyway, welcome everybody. Thank you, Eddie, for the introduction. Basically, I want to tantalize you guys with a statement that's not quite true as written, but we'll get into the nuances of what I'm trying to get at here. But I want to basically show you how to build a system that's a lot like the real numbers, but it has infinite numbers in it. And roughly how this is going to go. What do you mean infinite? We're going to start off with that. I need to give a little background also as to what we're talking about, how to make statements. So we'll have a little bit about how logic is used. And then I want to show you guys a really powerful result in logic that is called the Compactness Theorem, and show how it generates the things we're looking for, along with some extra remarks. So first off, what do you mean by infinite? Like, seriously, hasn't everybody known what infinite means since grade school? Well, naturally, I want to focus with the natural numbers. I think people are fairly familiar with what they are, what they're good for, but my question is, how do you define natural number? Like, can you say a number is a natural number if and only if it has this property? That's actually a fairly tricky question. About the best that people generally do when I try this on them is start with 1 and keep adding 1. Anything you get by doing that process is a natural number. This is basically the inductive approach. I don't think that's really quite satisfactory because if you give me a number, I have to just start with 1, keep adding 1 over and over, see if I hit your number or not. So, say, 37.2. I claim it's not a natural number because if I start with 1 and keep adding 1 over and over, I have to wait until I hit 38 before I realize I'm never going to produce 37.2. I want something a little bit better. Instead of talking about a pattern, I'm hoping I can just say, these are the numbers that are natural, these are the ones that aren't, give a nice clean sentence for the whole thing. So, not induction. Now, why is this handy? Because I can define infinity in terms of natural numbers. If you can count past your number, it is finite. That's a good enough definition as any. And have you dealt with infinite numbers before? Well, I imagine not, because the reals have this property called the Archimedean property. Usually it's not proven except in like lower level analysis courses, maybe junior courses. Sophomore, I'm not sure about this institution. But I don't like the Archimedean property, and I want to know, could I make a system that's sort of like R but does have infinites? And that's your spoiler. But I gotta explain what behaves like really means. So let's enter into some talks about logic and how we represent things in mathematics. So one thing that I think is not as frequently shown in beginning proofs courses is the idea of language. That different subjects need to talk about different kinds of things, and they use different symbols. Some subjects add, subtract, multiply, divide. Some subjects talk about edges and vertices of graphs. So what I'm going to do is introduce a concept called language that lets us say what kinds of things we're allowed to write in formulas. So languages have 3 portions. There is a set of functions. These are the things you are allowed to write to stand for functions. They take in inputs, they give back outputs. R tells me what I can use for relations. Relations take in inputs and then return true or false. And C, constants. Some constants are particularly famous, like pi e. There are some others. So for instance, for some languages spoken all over the world, yes, expect to see a few more of those silly puns and jokes in this talk. The language of sets is actually quite simple. You only ever use a single relation, membership. You say a set is a member of another set. There's no built-in constants. Some people throw in the empty set as a constant, but You don't need it. You can define what the empty set is. And there's no built-in functions. Because you can define the things people use, like power set and other such concepts. Orderings. All I need is a symbol to stand for one thing being less than another thing. How about something with more than just a relation? For people doing abstract algebra, groups. You usually have two functions, multiplication, inverse, and you have a constant which stands for the identity element of your group. And by the way, if you haven't had the exposure to any of these concepts, you're welcome to ask about them or presume that they don't matter too much, and it's for the sake of example. But I want to show this so that this really works on a number of different fronts of mathematics.
Like, why were there no functions on the sets?
So I'm technically writing down sort of the basic bare bones stuff that you would need. And if it's definable, I'm choosing not to put it in.
Okay, all right.
So when logicians talk about the language of set theory, they want the simplest language they can so that their proofs are shorter. So if they can prove something works for membership, they're done. They don't have to prove it for membership and power set and subset and...
Okay, got it.
Yep. Technically, inverse is definable from times, but oh well. Anyway, ordered fields. This one's big. Two functions, plus and times, an ordering relation, and usually you have two constants standing for the additive identity 0 and the multiplicative identity 1. If you throw out the less than, you get the language of fields. And this is pretty much the most important thing we're going to use because we're going to look at the reals as using this kind of language. And as a remark that sort of goes with what you said about set theory, minus and divisions are defined in times of terms and plus and times. The other problem is that plus and times are defined on all pairs of real numbers, whereas division is not. So I only want to write down functions that actually are defined on all the inputs for technical reasons. But the thing I want to warn you about, just with language, it's only telling you what symbols you have. It's like what the letters of your alphabet are. But just knowing what the alphabet is doesn't tell you how to write words or to understand the meanings of words. But you got to start somewhere. Like, I got to know that if you're writing down something, that at least it looks plausible. Well, once you've got a language, you can actually put them together and make formulas. The words, the sentences of your work. Variables. Take whichever letter system you want for your variables. I don't care about Greeks, Romans, Hebrew. Constants, functions, and relations from your language L. So different languages can produce different formulas. But usually the language that's associated with a formula is fairly clear from context, if we don't specify it explicitly. Equality is always a relation that we're going to use. There are certain logicians who say, what if you don't allow the equal symbol in your language? I think it's so present in all math, it's going to be there. Your basic logic connectives. And, or, with V and wedge, negation, drawn however you want. Some people use twiddle, I've got the little hook. Implication, and if and only if. And then, possibly the most important thing, quantifiers. For all and there exists. We don't have as big of a crowd here today, but just out of curiosity, is there anybody who hasn't worked with quantifiers and formulas before? All right, preaching to the choir. Okay, so basic examples. The formula sigma, for all x, x equals x. This works in any language. It has no free variables, and even more so, it's true. Last I checked. Okay, that I think I may have hit twice, but h of c says there exist a and b such that a times a plus b times b equals c times c. Well, That doesn't make sense unless you have plus times in your language somewhere. What do you think HFC is trying to say? There exists an A and a B such that A squared plus B squared equals C squared. It's saying C is the hypotenuse of a triangle. Hence H. And R of xy, saying x and y are reciprocals. So notice I don't have to use the division symbol to specify division. I can make an equation like this. This, P of n. N is greater than 1, and you cannot find A and B, which are between 1 and n, and multiply to form n.
N is prime.
Sounds good to me. It's saying n is prime if we're dealing with integers. So yes, if the variables stand for integers, this precisely means primality. But what about real numbers? If A, B, and n are just reals, which n is this true for? In other words, which n's bigger than 1 cannot be factored into two smaller numbers?
Infinity?
Well, infinity is not a number yet.
Okay.
Wait for the end of the talk. How about n equals square root n times square root n? If n's bigger than 1, these are both between 1 and n. So if I'm dealing with the reals, this is always false. The moral of the story? It depends where the variables come from to determine whether the sentence is true or false for the formula. And the usual term for this in your basic proof courses is called the Universe of Discourse. We can do a little better than that. Let's actually provide a way of specifying what the universe is, with applications like abstract algebra in mind. So I've got a language. A structure for it consists of the following parts. I give a universe set. This is the set the variables can take values in. So basically the universe of the reals or the universe of the naturals or other such things. And then what I have to do is also tell you what the symbols actually mean. So a function symbol gets a corresponding actual function, which frequently to denote it as a different thing is written F superscript M. M's interpretation of the function symbol. Each relation gets its own interpretation in R to the M, and each constant gets its own interpretation in C to the M. This is a mouthful of definition. Let's look at some examples of it. The reals, for example, are a structure in the language of ordered fields. Their universe is the collection of real numbers. What does the plus symbol mean when talking about real numbers? It means the addition you know and love. The function that takes two numbers and returns their sum. When the constant symbol 0 actually refers to the real number 0. The integers are another such structure. Oh wait. Oh yes, they are a structure in the language of ordered fields. They do have plus times, they have less than. They're not a field. Oh well. As far as the language goes, they're fine. They've got all the right symbols. So going back to this formula, I would say that in the structure of the integers, this is true for the prime integers. And in the structure of the reals, it's always false.
How do we feel about negative numbers here?
Well, negative numbers would not satisfy P of n because they fail the first condition. N is not greater than 1.
Ah, okay.
However, I'm really hinging on the fact that that greater than symbol is being interpreted the way you're used to. If I take a different ordering, this changes its meaning quite entirely. And as an example of this, because I really wanted to make a problem dealing with the language of love, my universe here consists of just a single member, and it is heart. I will tell you that the constant symbol 0 and the constant symbol 1 both represent heart. In fact, there's nothing else they could equal. That's the only thing in my universe. If you add heart and heart, or you multiply heart and heart, you get heart. Oh, and heart is not less than itself. That completely defines what less than means in this structure, because there's no other elements to compare. So it's basically the ring with a single element, and with no ordering. Well, that is a structure in the language of ordered fields, but it certainly doesn't have the properties you expect of ordered fields. For example, 0 equals 1 in this structure.
I'm kind of confused about the constant. You don't have a... So I understand, like, if I have division and plus, how you have a constant. Or if you have... So I guess I don't... What do they mean by a constant?
A constant is just any designated element of your universe. Like, a symbol you can refer to... It's a symbol you can write in formulas to refer to a fixed number. It's going to be the same every time you write formulas in that structure. So...
But it's not necessarily an element of your set?
Oh, it is. It's just the...
So it doesn't have any special properties, it's just...
Nope. It doesn't have any special properties, it's just, in general, you cannot refer to any specific elements unless you just use arbitrary variables, or if they're denoted by constants.
Oh, okay.
So like, if I'm proving things in groups, I can't just pull out random elements of the groups. I have to call them by variables like x and y, you know. Let x be an arbitrary integer. But in group proofs, you can say the identity element. The reason you can do that is because we've specially chosen to single it out as a constant.
And generators.
Exactly. Or generators, for example, is another good example in algebra. So, yeah, so you're not allowed to reference specific elements unless you've chosen to set them aside as constants. Okay. But anyway, the moral here, just because it's a structure for a language doesn't mean it has the properties you come to associate with said symbols. So our next bit is going to be fixing that. I'll tell you how to specify the properties you want. And that's through theories. A theory is just a set of sentences. Formulas that don't have free variables in them. So the sentences of the theory are the properties you want to be true. And a model is a structure which makes them true. So, for instance, let's say I want to talk about partial orders. Oh, yeah.
What is a free variable?
A variable that has not been bound by a quantifier. So, something that has to be plugged into the formula before you can interpret truth or falsehood. So in P of n, I had to plug in n before I could even determine truth or falsehood, but a and b were quantified. Is that good?
Yeah.
Okay. So what are the two results that define a partial ordering? The symbol has to be irreflexive, which means no quantity is less than itself, and it has to be transitive. If x is less than y and y is less than z, it follows that x is less than z. So these two sentences right here are the things that every partial ordering should satisfy. And this set of two sentences is the theory of partial orders. Nice that it's a finite theory, and the sentences are fairly easy to write down. So for example, our naturals, integers, etc. are all models of the theory of orderings. And different models. For example, naturals have a least element, and the integers don't. The rationals are dense, and the integers aren't. So, being models of a theory doesn't necessarily specify absolutely everything that's true or false. Just certain basic properties. The theory of groups says, the first sentence says the times has to be associative. Those two products have to be the same for all x, y, z. The second says the identity has to yield x, whether or not you multiply it on the left or the right. And the last says every x has a corresponding y which multiplies to give the identity. So that is the theory of groups. And groups are just models of the theory of groups. You want commutative groups? Throw one extra formula into the theory. And you've got the theory of abelian groups. And now I can actually get to the question I want here. Let's say I take the theory which consists of all sentences that the reals satisfy. This is not a finite theory. This is an infinite set of statements. I want to know, can I make a model of T which has infinite numbers? So it satisfies all the formulas that the reals do, except that it's got numbers bigger than 1, 1 plus 1, 1 plus 1 plus 1, and so forth. Oh, and these make sense because 1 is a designated constant of the language. But 2 is not, 3 is not. I guess I could throw them in, it wouldn't help matters. And the problem is, I don't know how to write a single formula that says x is finite. So, whether one exists, I'm going to forestall that for later. But such a formula, if it's there, then the theory says 1 is finite, 2 is finite, 3 is finite. But in the absence of such a formula, it's difficult to determine whether there is a theorem that says for all x, x is finite. All right? And now, the tool that's going to work for us here. The compactness theorem is a huge result in first-order logic. It says a theory has a model if and only if all of the finite subsets of the theory do. It doesn't tell you how to get the model. It's one of those non-constructive results. Those of you with enough experience in random things like the axiom of choice would be able to eke out at least some sort of construction, but it's not pretty. In fact, I believe the compactness theorem is equivalent to the axiom of choice. But the advantage of this is that finite sets will be easier to model than infinite ones, so we'll use this to get models. And I want to show you two big examples of this. The first, four-coloring infinite graphs. So, in case you're not too familiar with graph theory, graphs consist of vertices and edges. And for the sake of getting the presentation clean for what we're about to do, I'm going to think of edges as being a relation. So if x and y are related, that means they have an edge between them. And if they're not related, they don't. Fair? And this result, which I believe came up in a previous math club talk, the four-color theorem. Every finite graph which can be drawn in the plane with no crossing edges can be colored with four colors in such a way that no edge has two equal color ends. To infinity and beyond. Let's use this to prove that infinite graphs that can be drawn in the plane can also be colored in four colors. And interestingly enough, we'll be able to do this through logic means. But in order to start applying logic to this at all, I got to come up with a language for graphs. It's actually quite simple. I'm going to have a single relation, the relation standing for edges. And my universe will be vertices. So basically that. And I also want colors. So I'm going to model colors by using a relation for each of them. These are going to be relations that take a single argument. So C1 of x will mean x has color number 1. So whichever four colors you find favorite. Maybe C1 is x is red, C2 of x means x is blue, C3 of x means x is green, and C4 of x means x is hot pink. I needed a funny color. So, I can use these relations to talk about the colors of vertices. And I want to make a theory that says this graph is properly four-colored. It's going to have a few formulas in it. The first one is this. What do you think that's saying? For every v, either C1 of v holds, or C2 of v holds, or C3 of v holds, or C4 of v holds, it's saying every vertex has to have at least one color. What do you think the next formula ought to be? Not that there is a next, but something that should be in there.
If the two vertices are related, they're different colored.
Yeah, I actually wrote that as my third one, but that's definitely supposed to be in there. The next one I put in, you can't have two colors. And actually, I'm cheating. It's a long formula, so I'm just going to write that. The reason why is because it's really long. It's for all v, not C1 and C2, and not C1 and C3, and not C1 and C4. There are 6 possible pairs of colors you need to outlaw. So this would overflow like crazy, and I'm writing that. And the third one is what Eddie mentioned. For all v and w, if v and w have an edge, then, similar cheating, v and w do not have the same color. Okay. But those 3 sentences are all I need to say this graph is properly four-colored. So under that, I now have an infinite planar graph that I would like to four-color. Basically what I want to do is figure out, is it possible to make it a model of the theory of four colorings by determining the 4 relations. Determining who gets color 1, who gets color 2, who gets color 3, who gets color 4. Well, what I need to do is I actually need to do a little work so that my language, etc., actually tells me stuff about this graph. So bear with me on this. This is a fairly common practice in logic, but it's weird the first time you see it. I'm going to create a constant to stand for each vertex of the graph I want, so that I can effectively refer to the vertices of the graph. I won't be able to make a formula that says the only vertices of the graph are given by the constants. But, oh well, it won't matter. And I'm going to make a sentence that just says the vertex referred to by constant v and the vertex referred to by constant w have an edge between them. So phi e basically says the edge between v and w is in this graph. Fair enough? Actually, it just dawned on me, I forgot one thing. I should also make a sentence for the edges that don't exist that says not e this edge. I don't want to just force certain edges to be in the graph, I also want to force certain other edges to be absent. But okay. And now I'm going to make the theory. It has the theory of four colorings, and also the requirements that every edge from my intended graph has to be in whatever graph I'm studying. Okay? I have to do this because I'm looking for models of this theory that aren't necessarily G. Fair enough? So effectively, my problem's done if I can show that T has a model. But T's an infinite theory if G had infinitely many edges, because it's got infinitely many of those phi e statements. I'm going to use compactness to show it as a model. So let's take a finite subset of T, only finitely many formulas. So it only has finitely many sentences that require edges to be there. Let's say that E star is the collection of edges that this forces to be in the graph. So T star, I can assume without loss of generality, it's got all of the sentences from T call, because there's only finitely many anyway. And it's got this form. So how do I model that finite subtheory on the right? I'm looking for a four-colorable graph, i.e. a model of T-col, which has the edges of E star. So the question becomes, well, how do I find a graph which is four-colorable and has only those finitely many edges in it? Well, turns out to be not too bad. Take the original graph I started with, keep the same vertices, and only put in the edges of E star. Just throw out all the others. It's not technically a finite graph because it still has infinitely many vertices, but there's only finitely many edges, so all but finitely many of the vertices are isolated and you can get rid of them. So, does it make sense if I say it's essentially finite and planar? Because G was planar. Okay, well, it's finite, it's planar. The four-color theorem says it has a four-coloring. So it is my model of T star. So, all the finite subtheories have models. T has a model. QED. And actually, arguments like these are really common when trying to extend a result from all finite cases to infinite cases. And a lot of them fulfill this same kind of pattern. Throw in extra relations and extra constants to capture the structure you're trying to mimic, and consider only finitely many at a time in a finite subtheory.
How is, we call this the compactness theorem that allows us to do this. How is compactness related or not related to compactness in like topology and real analysis and calculus?
That's a loaded question. I can mention a little bit about it. So I would say that ultimately the theme of compactness, even in real analysis, is boiling down an infinite collection of covering sets to only having to consider finite collections. So here there's an infinite problem is solved by considering arbitrary finite ones.
All right.
Though there is a way of putting a topology on sets of sentences such that you get open covers by sets of sentences and you consider a finite subcover. It's more than I want to go into, but it does happen. Okay. So yeah, the two results are actually related and it's pretty nuts. All right. Now the second example I want to use this on is the main $64,000 question. Let's make a model of the theory of the reals that has an infinite element. So, as we previously established, the reals are a ordered field. They have all the symbols of the language of ordered fields. They have a plus, a times, a less than, a 0, and a 1. And let's say T is the theory of the reals. Just all the sentences that are true in it. I won't be able to list them as nicely as I was all the previous theories. And what I plan to do is find a model of T that has an element bigger than the natural numbers. So what I'm going to do is I want to talk about that element that I hope is infinite. I'll make a new constant for it. And what I'll do is, for each natural number n, I'll make the statement phi sub n basically saying C is bigger than n. But since I don't have n in my constants, I have 0 and 1, I'm just going to say 1 plus 1 plus 1 n long. So each of these phi n's is a finite length formula. And it has no free variables in it, only constants and known relations. Oh, and the plus operation. So my theory is going to be, take all the statements that are true in the reals and throw on these sentences. Throw in C is bigger than 1, C is bigger than 2, C is bigger than 3. So my theory was infinite before, it's even more infinite now. And if I have a model of this, it's the thing I'm looking for. So Let's show it has a model by taking, oh, it should be an arbitrary finite subset of T in. My apologies, but anyway. Take an arbitrary finite subset, and because it's a finite subset, it only has finitely many of the new sentences I threw in. So it's got a biggest one. Let's say capital N is the biggest natural number it refers to. So my theory, my T star, contains a few sentences from the theory of the reals together with C's bigger than 1, C's bigger than 2, C's bigger than 3, up to C's bigger than capital N. Well, I don't think it's too bad to make a model for this because I'm only requiring that C has to be bigger than capital N. What should I set C to be? N plus 1 works just fine. So interpret C to be N plus 1. Now this model doesn't work for the whole theory Tn, but it works for the finite subportion. And that's it. Effectively, the compactness theorem's proof shows that if you have a model of all the finite pieces, it tells you how to stitch them together into a supermodel, which is much fatter than a usual supermodel because it really incorporates all the infinite statements. Cue end of bad joke. Okay? But how about that? We have a model that has all the theory statements of the reals true, but has an infinite constant. What we tend to do is we say that the things that aren't the standard reals are called the non-standard reals or the hyperreals. So C is an infinite hyperreal number in capital M. Well, there's other hyperreals and there's other infinite hyperreals. Why don't you tell me, what do you think's another infinite what's another infinite hyperreal? I've got 1. I've got C. Yeah, C plus 1. I can do that because I've got plus and 1 in my language. I can also do C plus C or C times C. And actually, since C is bigger than 1, you can prove C plus 1 is smaller than C plus C. And C times C is even bigger.
Can you say something like C times C, or C times something equals 1?
Sure. Actually, that's exactly it. C must have a reciprocal because the theory of the reals has a statement that says every positive number has a reciprocal. It's true in the reals, right? And C is clearly positive because it's bigger than 1. So C has a reciprocal. So yeah, there's a 1 over C. Now here's the catch. C is bigger than all the natural numbers. 1 over C is less than the reciprocals of the naturals, but still positive. 1 over C is an infinitesimal quantity. Oh, and it's not the only one. You could divide it by 2 and you get another infinitesimal. 3 over C is infinitesimal. You can prove that 3 over C is less than all the 1 over n's. Actually, any finite real number over C is still infinitesimal. So you have a huge, huge quantity of infinitesimals. In fact, just to throw something really nuts out there, between any 2 reals, you have an uncountable collection of infinitesimals. The non-standard reals permeate like crazy. Oh, and you know you've got C, you've got C plus 1, you've got C plus 2, you've got a whole copy of the real line C plus all reals that sits way off in infinity land past the standard reals. The non-standard reals are huge. And this actually leads to a study called non-standard analysis. Now that you have infinitesimals that are positive but tinier than reciprocals of reals, things like dy and dx in calculus Abraham Robinson and other people managed to show that you could get a coherent theory of calculus where dy and dx aren't just limits, they're actual positive hypernumbers. And in non-standard analysis, the proof of the chain rule really just is write the two derivatives and cancel the d. Granted, there's a lot more logic finagling, and it's been shown that non-standard analysis can't prove things that standard analysis couldn't. It may give you different ways of thinking about it, but cannot give you new theorems. It just may make it easier for you to prove theorems that you would have gotten otherwise. So there you have it. This is used for something. And it was a real big logic play around this time. Like, oh my god, people were jumping on this as if it were the next big thing. Excitement sort of died down, but there are people in this. And as some last remarks about this model, I've given you a few cool things, but what this model shows is actually some very powerful results about the reals. I cannot make a formula that says this number is finite. Because if I could throw the statement, all numbers are finite, into the theory of the reals, and then M, which is a theory, which does satisfy the theory of the reals, would have to satisfy that. All its numbers would have to be finite. But M has an infinite number. So I can't make this formula. That's why finiteness is so tricky to do. Okay, technically you can do it if you use things that aren't first order, if you allow yourself to quantify over sets in addition to individual elements. Good. That's it. So I can't do finite. I can't do naturals. Because if I could define finite. And normally in what real analysis courses do, they do manage to prove the Archimedean property, but they use completeness. Well, it turns out all the axioms of the reals are clear first order statements, except for completeness. But I've just shown that in first order logic, you cannot put the Archimedean property into the theory of the reals. So the completeness property cannot be done in first order logic. Nor can the principle of induction. And if you find these kinds of topics particularly fascinating as to the power of what a logic can say, using logic to unify a few theories and to get models of all shapes and sizes, there is a discipline for this, and it's called model theory. And I thank you all for your time, and I ask if you have any questions. Go. Yeah.
So the completeness theorem, or the compactness theorem, that's an actual theorem.
Correct.
But you said it's equivalent to the axiom of choice?
That's right. Okay, fine. It is a theorem under the axiom of choice. But most mathematicians, by and large, buy the axiom of choice now.
It's a theorem on, so you're assuming the axiom of
It's
choice?
a theorem in Zermelo-Frankel set theory plus choice.
Okay.
Yeah. You'd be very hard pressed to find that many mathematicians who don't use it as one of their axioms for reasoning.
Yeah, no, I know axiom of choice is always used. So my question is, so the compactness theorem, you said it's equivalent to that.
I believe so.
But it's an actual theorem.
Okay, fine.
Is it a proof or?
It is a theorem under the assumption of CFC. You can prove without using choice that the axiom of choice and compactness are equivalent.
Okay.
So if choice is in fact one of your axioms, then it's a theorem. I am not claiming that compactness can be proven without choice. That is not true.
Okay, no, that's
okay. Yeah. And that's really more highfalutin set theory wankery.
Okay. And you also said that there's stuff that non-standard analysis can't prove that real analysis can't.
No, it turns out they're equal. There is a result. The result in logic terms is that the theory of non-standard analysis is exactly the same for the standard reals as it is for the theory of standard analysis. In other words, if you write a formula that only has standard reals in it, and only standard real concepts, then it is provable in standard analysis if and only if it is provable in non-standard analysis. It's just that the non-standard analysis can use extra tricks of the trade, like infinitesimal, to come up with the proof. So yeah, there's plenty of nut stuff that goes on, because the less than relation, the ordering, becomes particularly strange because, as I've said, completeness can't be done in first order. So the ordering of your naturals, the ordering of your non-standard reals is not complete. You don't have supremo of all sets that have upper bounds. So yeah, a lot of the results of standard calculus that deal with completeness, like intermediate value theorem, need to be adopted with a great deal of care beyond where I want this talk to go. Okay. You want one random tantalizing result in addition to this? So, I can make a model of the integers with infinite integers by similar techniques, and I can do it in a way such that I have an integer for which 2, 5, 11, all of the even indexed prime factors are its prime factors. I can make a number which is precisely the infinite product 2 times 5 times 11, etc. The way I do that is I make instances in my theory that says 2 divides this constant, and 5 divides this constant, and 11 divides this constant, and 3 doesn't divide it, and 7 doesn't divide it. Any finite collection of those sentences has a model in the standard integers. All right. Well, thank you again.